That's big enough, right? Okay, so I will start. Good morning, everyone. So today we will start looking at the ways to speed up the computations in Python. There are different ways to do it, and one of them is using the parallelization, which is the topic of the next hour and a half. So in this chapter, we will talk about how to parallelize your Python code and which module to use. And after this workshop, you should be familiar with various types of parallelization and have some knowledge about multiprocessing and multithreading. So if you look at the performance of one single CPU core, I mean, basically it's stagnated during the last 15, 20 years. However, the need for better performance is not decreasing. So what people do is that they use multiple cores, essentially running programs in parallel. Parallel processing is normally based on either multithreading or multiprocesses. And these two naturally becomes the two main models of the parallel computing. So first, the multithreading, which is based on shared memory parallelism. This means the threads, they do separate work, but they communicate via the same memory, and they write to the shared variable as well. However, the multiple threads in a single Python program cannot execute at the same time. Due to the so-called global interpreter lock. We will talk about this lock later in detail. However, this is not end of the world because, for example, for I/O kind of tasks, running multi-threads in Python is possible and efficient. In addition to that, if you're using external libraries written in other languages like C, C++, for example, in NumPy, Cython, and you can still use multithreading. The second one is multiprocessing, which is based on distributed memory. In this case, each process has its own memory segments and do not share data among each other. But sometimes data is needed from another process. In such a situation, communication is needed. And usually it's via, for example, message passing interface, MPI. Each process could contain one or more threads. And the different processes do not have to be run on the same CPU core, and they can even run on different machines, computers. One thing is that to creating or destroying one process takes more time, so there is a little bit more overhead to run processes. And running multiple processes is very effective for compute-bound tasks. So apart from these two, excuse me, there are more to mention. First, it's a so-called embarrasing parallel program. So sometimes the program you are dealing with can be decomposed into independent tasks, or the data can be independent. So there's no shared resources, no communication is needed. For example, typical example like Monte Carlo analysis or ensemble calculations for in numerical weather prediction. Discrete Fourier transform is also one example. Convolutional neural networks. Also, if you apply the same model on multiple data sets, that's also embarrassing parallel program. So if you are working with such a program, you probably will achieve very high performance using parallelization. Then the second type is about GPU computing. So this framework, they take advantage of the massively parallel compute units, which is available on the GPU. And it's ideal when you have a lot of arithmetic operations. Hello? We do have an episode in the optional material for the GPU computing. And for those who are interested, you can take a look afterwards. Another type of framework I would like to mention is things like Spark or Dask, which is also sometimes called distributed computing. So in this case, the framework is based on a master-worker parallelism. So the master builds a graph of task dependencies and execute the tasks in proper order. I mean, the workers, they do that. You will hear more about Dask from my colleague. I think tomorrow we have a session about that. Just a couple of words about concurrency. So in Python communities, you hear this a lot. It means, any types of simultaneous processing, including threads, tasks, and processes. A concurrent task can be executed in any order, but with the same final results. And also a concurrent task can be executed in parallel, but doesn't need to be. In this lesson, we will use the concurrent future module, which provide the implementation of both thread and the process-based executor for managing resources to run the concurrent tasks. And you should be aware that to achieve concurrency sometimes is difficult because there are problems like race conditions and deadlock. Yeah, so just to summarize here a little bit. So parallel programming requires that we have a different mental model compared to serial programming. Many things can go wrong, and you could get unexpected results, and it's also very difficult to debug. So it's important that you understand the possible pitfalls before doing the work. And I recommend that you watch the video from Raymond Hedinger. Yeah, I just mentioned the global interpreter lock before. So the designer of Python language, they made this choice that only one thread in the process can run actual code. So this means, for example, approaches that work in other language like C, C++, Fortran may not work in Python. And the reason to have the GEO is because the memory management in Python is not thread safe. Of course, this is not good for parallelism, but as I mentioned before, there are ways to avoid it. for example, using external libraries like NumPy, SciPy, Pandas. And also for the input-output tasks, they release the GEO. And if you are using multiprocessing, this also release the GEO. Yeah. So for the multi-threaded library, like NumPy, SciPy, so basically they are built on external library like LARPAC, FFTW+, which provides subroutines for linear algebra, FFTs, etc. And these libraries are written in C, C++, and that's the reason why they are not affected by the GEO. And technically, they also support multi-threading during execution. So, for example, NumPy will use multi-threading by default. And what you need to do is just set the environment variables OMP threads. In this case, then the program will run in multi-threading mode. And this is how you do it just do that in the terminal. This is for bash, depending on if you're using other shell, it might be set OMP num threads. And I'm not 100% sure, but for Windows, I think this is also how you set the OMP num threads. For multi-threaded I/O problem, this is how typically an I/O-bound application looks like. So as you can see, the problem is most of the time the CPU is just waiting for the request on I/O, which is not efficient. And if we can run multi-threading, and this will be how we speed up. Basically, we overlap, let's say, the waiting and CPU processing to achieve speed up, to achieve performance. To run multiprocessing module in Python, which is very similar to running multithreading in terms of the APIs. And one of the simplest way is to using the multithreading via the pool object and the pool, calling the parallel pool map function. And actually, what you could do is you could also use the concurrent future processing pool executor, which is basically a wrapper of multi-threading pool. In this case, you unify the threading and the processing interfaces. Just a few words about if you're running multiple arguments. Sometimes the functions, they take multiple arguments. In multi-threading, you need to change it to pool start map function instead of the pool.map function. There are other ways to do it. For example, you can use a function adapter. So you could use a function adapter to run multiple arguments, or just simply use multiple argument iterables. And one more thing about running multiprocessing is functionalities within multiprocessing requires the main module to be importable by children processes. This means, sometimes some function may not work in the interactive environment, for example, like IPython or Jupyter Notebook. So we only talk about using the concurrent futures, but there are a number of other methods which can be useful, including things like process and queue. With these methods, you can have direct control over individual processes, but this is not the topic of the current lesson. But we have material prepared in the C also section. Yeah, next. Next, we will talk about the message passing interface, MPI. As I mentioned before, sometimes the processes, they need to communicate. And then we need to use MPI, which is a standard workhorse for parallel computing. So the idea behind MPI is that, so tasks, they have a rank, and which is usually numbered from 0, starting from 0. Each task has its own memory, and each task can run multiple threads. Tasks communicate and share data by sending messages explicitly. Yeah. And the MPI4Py, which is the Python binding for message passing MPI standard. And here is one example of Hello World MPI program in Python. So in the beginning, you need to build this so-called MPI.com _word, which is the communicator, which you must have. And then you can get the size of this communicator, and also you put the rank for each process in the communicator. And to run the program, you need to call the MPI run command, which comes with the MPI library installed. So the MPI standard contains a lot of functionalities. But the most basic fundamental one is the point-to-point, which includes a send and receive, so from one process to the other. There are other collective commands, for example, like scatter. In this case, the data on the rank 0 sends the data to rank itself and 1 and 2. And gather is the opposite operation, which collects data from 0, 1, 2 to itself. Broadcast is the root rank sends the same data to all the other ranks. And also you have reduction operations as well. Here is the code for each operation. You can take a closer look during the exercises. Yeah, I think then it's time for exercises. So the first exercise is about multi-threading external libraries. So here is the piece of code which simply does a matrix inversion of a size 4000 by 4000. And you can try setting the environment to different number of threads and look at the speed, so to speak. The second access is a comparison between IO bound and the CPU bound. Here in the exercise, I will just using a sleep function to simulate, let's say, an IO bound process. Yeah.
What is the difference between the IO bound and the CPU bound?
I mean, the IO bound usually is, things like reading and writing to disks or waiting for like internet requests, things like that. Well, CPU bound is like computation, basically. The third access is about race condition. And you can run it and see. Oh, wait a minute. Yes. Simply just run the program and see what happens. And then just think about how can you solve this race condition problem. Yeah, then it's just one problem of computing the numerical integrals. Yeah, it's just using multithreading or multiprocessing and compare the difference. So in this case, for the multi-threading one, basically due to the GIL, you will not have speed up. Yeah. And the last is about the word autocorrelation example project. I mean, you don't need to do all of them, but yeah, just take your time and yeah.
Yes, it is 10:40. It's for the Central European time. Let's start the second part about this morning session. It will be Ashwin. We talk about the benchmarking, profiling, and optimizing the Python code. Please.
Thank you, Yongle. Yeah, so this is going to be an episode a bit more than an hour, and we'll talk about some tools and methods to analyze performance and to fix it. Just to give an overview of what's going to happen in this session is that we'll start with benchmarking first, and quickly there will be a short exercise. And then after the exercise, we'll talk what profiling is. We'll explain all that later. And then there will be a slightly longer exercise and on to optimization where there will be just demos. And then we'll wrap it up for today. So yeah, so the goal is to understand what these all terms mean and to know how optimization can be done. Like we'll see how it can be done towards the end. But if you're building a new application, you need to make sure certain things are in place before you even start, optimizing or trying to tweak your code. in plain English. You need to make sure that the code is correct, and that usually one can write tests, either automated or manual tests. So some test case where you're sure this output can be repeated all the time. And only then you should think of optimizing it. Otherwise, you can get a faster code which gives wrong results and it is of no use. And before optimization, we should always measure the code. And that is what we mean by benchmarking and profiling. So measure and don't guess. If you make it based on assumptions, you will just have surprises. You try to make one line of code really fast and the whole program doesn't speed up. On to benchmarking. So benchmarking is how you do performance analysis, either for the whole program or just a part of code, part of a program. It can be a single line of code, a bunch of lines, or a function. So for example, a very naive way, if you want to keep it simple, this is how you'll do it in any language. You will try to record what the current time is just before a code starts. And then you run some piece of code here. There is some function which does something. We don't have to know what it does. And then once the result is done, or if it gives a result, or we record another checkpoint, and then we subtract it and see what the difference is, and that's the runtime for that function. And this can be implemented in any language, and in Python you can do it like that. But there is also a very convenient Jupyter magic called time, or percentage time. That's how you write in Jupyter. So we can try to do something similar here. Let's try something which gives, hello. This is one way to do that. The other way will be if you write percentage time and then the piece of code, some function. So it does this roughly the same, but it also gives you some more details. We'll see what this means. But as a user, maybe you're just interested in the start and the beginning, and that is what wall time means. But we'll talk about what other CPU times mean later on. But this is just one measurement. And if you do this maybe once again, you might get a different result, right? So if I try to do this, some function again, then I get roughly the same answer, but a different value. So then it's useful to use this time it magic instead, which repeats this benchmark over and over again. And then you get a more reliable answer. So for this, here there is one example, but I'll just, for the sake of completeness, I'll do it for this sum function again. Of course, I was printing it, so that's why you get too many. So maybe it was not a good idea after all. Let's try this. So here we are building an array and trying to square the array throughout for every element. And we are making a benchmark, and we'll soon see what the result is. Like it's taking quite long time because it's repeating this benchmark until it knows it's reliable. So then you will get an answer in terms of mean plus or minus standard deviation. And this mean is an arithmetic mean, so it's how benchmarks are usually done. And if you repeat it, most likely you'll get, sorry, if you repeat this, most likely you'll get the same answer. So you could try the same with another function and try to see what happens yourself. And there is an optional exercise where we will reveal like what these other CPU times mean. So let's give it 10 minutes, let's say. Is that good? So 10 minutes for this exercise one, and then they'll come back and discuss it. All right. So I guess we'll continue. So I'll try to explain what's happening here. So I have the code running here in Jupyter Labs. So if I do this benchmark, that's the first question, like do it a couple of times. Do I get the same results? Surprisingly, yes. It shouldn't. Maybe I should increase the size of the array. Okay, so now it's different results, like it's of the same order, like milliseconds, but the time taken is a bit off. So that's what I explained before. Like if you repeat the benchmark using time.it, you get a more reliable, reproducible benchmark. Now it's actually showing it's not milliseconds even. It should take just a microsecond, a few hundred microseconds. So this one was absolutely an outlier. And the actual time taken is around 375 for this, but in this compute node in Lumi. And then they will also show like how much it can, go plus or minus based on statistics. Then, so with time.it, you can get a more reproducible result. So you'll get most often the same result, roughly. But then the third question is using time to read a file which is in GitHub. So it will try to ask GitHub to give this file, and then this GitHub will deliver it. So it takes some time. So what you notice here is it took a second, but if you look at CPU time, it took only 20 milliseconds. So the CPU was working very shortly, like it put the request and then went into sleep mode, like it was waiting for the request to come back. And then when the request comes back, it does something. Okay, it opens up the box, see the file, something like. But for the user, it took a full second or a bit more than a second. So this is what I try to explain here. Okay, this part is explained like right. Yeah, I'll come back to those, but to bring this home, when you run the first time, like you see that the CPU time is of milliseconds and the vault time is also of milliseconds. So while the execution was happening, the CPU was also working at the same time. So which makes with which we can conclude that the first operation, which computes a square of an array, was CPU bound. So it is waiting on the CPU to finish it. Whereas this one, which does a network request, was IO bound. So the CPU doesn't have to work so much, but it takes longer. So over here, it doesn't matter if you're using a very compiled language, because the slowest part is the network. You won't get any faster than what you get from Python even. But IO bound operations are not limited to just network. It can also happen due to slow file system. If you have a slow hard disk to read and write, it might happen. Or you might be using very inefficient file storage formats, something like a text file, a very long text file. That can also happen. So that you are just waiting on reading and writing. But also to explain like why this is happening, like why you get different results if you throw the time benchmark, just a single benchmark. That's because the state of the computer can be changing all the time. There might be different background processes running, like if I did this in my computer right now, like Zoom is running, and then Zoom can affect the benchmark. Hyperthreading might be activated, and hyperthreading can result in this process getting attached to a hyperthread, which is a computer thing. And often times when you have hyperthreading activated, you might get slower results, although it might be parallel. Memory and cache usage patterns, like where the array is actually assigned, and then if the array is operating on another array, and then those, like how the array is stored matters. It's if it's compactly stored, or if it's spread throughout the memory, or just a CPU state, like if it's heated up, that can also affect it. There are many factors, and these are often termed as jitter, and you want to avoid jitter while doing benchmarks. That's why we do repeated statistical measurements. We had some results in the HackMD, so I don't know what exactly it was going for one particular learner here. Like they got 0 nanoseconds. It could be because like it was very fast. And typically the clocks in the system have nanosecond resolution. It's possible in Python at least, or maybe it's, I'm not sure here. So it could be that the time method was using a clock with a millisecond resolution. That can also be the case. There is a time.perf counter method in Python. So it will be something like time.perf counter, and there is a perf counter nanosecond method. And this is also another clock which can be used as an alternative to time.time method. Right. So that was a bit about benchmarking. But benchmarking can only give you an idea of like if you know what to measure. But if you don't know where the code is slow overall, then it's tough to find bottlenecks, right? So that's why we have another method called profiling. So profiling, you use certain applications which attach to the execution of the program. In our case, the main program is the CPython interpreter. And then it analyzes the time taken for different parts of the code, different portions of the code. And then by analyzing this and saving this, it can help you identify where the bottlenecks are. So that's how profiling works. Profiling can also show other things than just the wall time. That's what the user observes. Some profilers can also analyze GPU time. So GPU usage, CPU usage, and like memory usage patterns can also be part of a profiler. Not all of them can do that. And then it can identify the start and finish of a function. That's what most profilers do, or a method. But some profilers can also give you line of code level granularity. So it can tell you what each line costs in terms of computational time. There are two different classes of profilers. I'll make this bigger. The first one is deterministic profilers, and the other one is sampling profilers. Deterministic profilers are sometimes also called tracing profilers. So what deterministic profilers does is it records every function call, start and finish, and then it actually attaches like it to the part of the execution. So every time the profiler is recording a time, you will get an overhead. But the good thing is it gives you a detailed information of all the functions. If you repeat it, it's often repeatable, so that's why it's called deterministic. But because it's attaching to the execution, it results in higher overhead, and it will be slower, much slower than doing a benchmark. So you'll see that the overall execution was maybe 10 times slower, and can also result in a lot of data depending on how much functions are getting called. Sampling profilers, on the other hand, is a bit of a statistical approach, takes a statistical approach. It doesn't track all the function calls. You can think of sampling profilers working as a separate process, trying to probe what's going on every now and then, looking into the execution. So as a result, you will have very low overhead, but it doesn't track everything. And for larger programs, it might be useful to use a sampling profiler. It's less precise, so it will miss out on some small functions, and it's also a small approximation rather than exact measurement. If computers are too heavy to understand this, like we can take an analogy, like somehow you are working for SL Metro, like for the Tunnelbana, and then you want to identify where the bottlenecks are, where the crowding happens. So then you ask a few select passengers to track their journey. So the deterministic approach is to tell the passengers to record each and every start and stop of a journey. So when they board the train, they'll send a SMS to the headquarters, and then when they exit the train, they'll write another SMS. But then they'll slow down their whole, commute. But sampling one is like, okay, they are relaxing, and every 5 minutes they get a notification to, okay, send your location. That's it. And they won't be bothered otherwise, so they don't have to think about it. So that's the sampling approach. Here are some examples of some popular profilers. See, profile and profile are built into the standard library. So that's what we'll use in the beginning. Line profiler is a third-party library, which is also a deterministic profiler, and it gives you line of code level granularity. Line profiler. C profiler, by the way, is also deterministic, but it gives you function level analysis. This one is also a very fast profiler, and this one is a sampling profiler. And the advantage of using PySpy is that you can track compiled code like Fortran and C code, which interacts with C, which interacts with Python through PySpy. And if CPU is not the biggest bottleneck and you're concerned about where the memory is blowing up, then you might need to look at memory profilers. Tracemalloc is part of the library as well. So you can use tracemalloc similar to how we were using time function in the beginning. So tracemalloc, you'll record a snapshot before and after a function, and then you'll see how much the memory grew. Memray is the sampling approach for memory profiling, and this is a third-party library. If you want to do everything like CPU and memory, then scaling is a good tool, and scaling can do a bit more than just CPU and memory profiling. So you can have a look here. This is a very early course material, so the descriptions are a bit sparse, but you can have a look after the course. So here is an example of a random walk. The algorithm tries to calculate the position. So this random walk algorithm, it's not very important to understand what's going on. It tries to use a random number generator to move a fictitious particle in one direction, either forward or backward. So it can be going one step forward or one step backward based on a random number generator. And then it should get to some place after a certain number of time steps. So if you use loops, this is how you will implement it. You write a an array complete with nothing, like just to initialize it with zeros. And then you start recording the positions for each time step as elements of the array, one by one, from 0 to n minus 1. But there is also a vectorized version, and that's part of the exercise. But I'll start by demonstrating how this will work. So profiling, and now I'll see if I have the no, I don't have the file here. So I have it cloned here, so that's the reason why I am trying to find it, the whole course material. But if you want to download it yourself, you can click on this big red button and then you'll get it on your computer. Or you can copy the link, and then that's another way to get it. Right. So one could try to execute a command line code in Jupyter. That you do that by starting with an exclamation. And then, so this is the same thing as running it in terminal. So what happens is it will run this code for the prescribed number of time steps, which is 1 million, and use the C profiler. It records all the function calls and sort it by total time. And you will see which line or which function is getting called most of the time. But this output is a bit hard to understand. So in order to visualize it, there are some external visualizers called Snake versus Tuna, which we are not going to show it here, but they need a file to read, and that is produced by adding this argument. So you see it's very long. Right. Scroll down here somewhere. Yeah. So if you add an output flag, then you will, instead of printing it out, you'll get it saved as a file. So that's a bit about cprofile. There is also a magic command called prun, which does roughly the same. So in order to do run prun, you need the functions which are imported. So I can, or alternatively, I can copy this here. So I have all the functions defined within JupyterLab, and then one could run prun, and then this is, and then a particular function. If you're just interested in particular function, they could do like that. And then you'll get roughly the same output with some other Jupyter related things going in the background. But this is a bit less useful as it is. So let's take a look at how line profiler works. So line profiler, as opposed to cprofile, gives you line by line recordings of how much time it takes. So here, what we are trying to do is we'll have to add this profile. So yeah, this is one approach. We can either add this profile decorator, and then we can try to analyze how long step and walk takes to execute, and then run it using this command line code. That's one approach. But since we are using Jupyter Lab here, I'll go for the second one, which is using this magic command called lprun. And you need to load it first using load X line profiler. So I'm going to do that. So I'll add profile here so that it knows that, okay, we are interested in this. Okay, I think when you're running with Jupyter Lab, you don't need this profile decorator if I'm not mistaken. So we'll just delete it, that part. So I loaded the line profiler, and then here, instead of adding the decorator, you can pass it as flags to this command. So that's the way it works here. Right. So what line profiler does, it analyzes those particular function line by line. So we can see the main function, which is walk, and you can see what percentage of this particular function was consumed by this line. For example, we see that, okay, incrementing the position using this line takes up majority of the time. So it could be either this addition which is going wrong or the step function. So what could be the problem here? Like, so that's the question, like why this could be slow, or can it be made faster? Sorry. So we see that the step, this line containing the step, so we can assume that the function call for step is the slow part. And then we look at this function call for step, we see that roughly half of the time is spent just importing this library. So if we can make this import statement go up here. And by doing so, we should be able to see it go faster. So if I run it again, I executed the code so that it's new again. And now you see it's slightly better, not great. It still takes some time to do this, but it's less than what it used to be. And you don't have half the time just importing the code. So that's what we see through line profiler. And now we have an exercise using the same script. And now the question is, can you use line profiler? And we combine also benchmarking. So you can start by copying the script over here, copying into your Jupyter Lab, and then try to use time it to benchmark walk and walk vec, which is a vectorized version. See which one is faster. Then you're asked to profile the walk vec function and try to find out what is the bottleneck. The bottleneck is already seen here, but do it yourself to see it, like which one it is. And then you need to swap these two lines and see what happens. So it's a slightly longer exercise, so I'll give you 15 minutes to try it for yourself. It's exercise 2 here. So 15 minutes. So we meet 35 minutes past the hour. All right. I hope you got some time at least to try out 1 or 2 questions, or maybe the whole exercise if you're lucky. But nevertheless, we'll start by discussing it, what you get. So here, one of the learners reported the results of the first question. Thank you. So you see that for walk function, you get a timing of 4.62 seconds for a big input size of 10 million. and 6 seconds roughly for vectorized version. So our intuition will say that we don't use for loops in Python and you get faster performance, but that didn't happen right away. So it's not always guaranteed. And this is also nice to check for other input sizes, like for 10 million and 1 million. A mistake, like the bane of all benchmarks, is like it's dependent on the input size. Sometimes you optimize for a small array size and it won't scale properly. So it's a good thing to always try small and big input sizes. So just a comment. But anyway, what you should get if you follow the instruction is given in the solution. So you here also is the same result. You get a slower performance with vectorized one, and then you see why that happens. But when you run the line profiler on walkback, and then the line profiler should give an output which shows that this particular line takes more than 99% of the time. It was actually unintentional when I wrote it. I thought it's a good approach to just use the random sample function. This is part of the standard library and not the NumPy's random library. So what this produces, it tries to sample from a very large population, as it's called, a very large population, 10 times bigger than what you actually need. So as to get a very random sampling. But this will be a list and not an array. So it's will be much bigger. So it's consumes a lot of memory. You would see that if you run scaling on it, you see how much memory it consumes. So the cure is to comment out these two lines and use this instead. So I do that here, and then I run the benchmarks again. So then one would see that instead of a few hundred milliseconds, it probably takes a couple of milliseconds. So this random choice function does the same thing, but it generates a NumPy array without an intermediate list. So that'll be much faster than doing this two-step generation. And of course, you'll see that here, like yet again, this step takes majority of the time, but it's not 99%. You get it. The distribution of the time taken by each line is a bit more spread out, and you'd spend some more time, some meaningful time doing the actual time integration, which is done by using cumulative sum here. Anyway, so that was a bit about profiling. I hope you understood what the purpose is. But once you do profiling and benchmarking, so you might have spotted a bottleneck in your code, and then you want it to go faster. For example, the thing that we did here, swap this line instead of that. That's a optimization that we did here. So unfortunately, optimization is very case dependent, it's problem dependent, data dependent. So it depends on how big the data is, how frequently a function is executed. If it's executed only once, maybe it's okay. If it's not optimized, or maybe there are some sub function calls which are executed much more, which you might need attention on. All those things come through profiling. You see that. But anyway, we try to give you some guidelines here. So the first thing you should think about is try to see if there is an alternate algorithm. Very often, a better algorithm gets you much further than trying to solve it through programming languages. For example, one thing which I can think about is the fast Fourier transform algorithm. So it was invented in the 60s, but until then, the classical Fourier transform will take order of n square operations. And once this trick was invented by mathematicians. You can solve for certain Fourier transforms in order of n log n operations, which is much smaller than n square. And here is another example specified here. Here it's described that if you're solving an eigenvalue problem, maybe the matrix is very ill-posed. If you try to make it symmetric, it might be easier to find what the eigenvalues are. And sometimes solving linear algebra problems, you should try to use a less costly approach rather than the inverse. Inverse of a matrix is very expensive, and there are iterative approaches rather than using a direct inverse, which might be approximate and might get the solution faster than what you have. So here is another example of singular value decomposition. This is typically used in climate model data analysis. And the problem with this approach, if you try to reconstruct the decomposition of an array, it results in very large arrays. So for example, just to give you an idea what singular value decomposition is, it's the more generalized representation of how to decompose a rectangular array because in eigenvalue problems you should have a square array to find the eigenvalues are, whereas in singular value decomposition the array can be long or tall. So that's what it does, and it gives you 3 arrays as output. So for example, here you have a data which you want to find what the singular values are. So if I try to run that quickly, over here, I initialize the data, try to find what the singular values are. For example, by doing so, let's call it SVD just to make. So it does it, but what you get is you get 3 arrays. One is called S. The other one is called U. And the other one is called VH. So because this solution is very big, it takes a long time to build from this very small array. You get a 4,000 square array. That's the reason why it takes a long time. But if you are not interested, if you're just interested in the S, this or sigma as it is called in singular value decomposition, you can just pass this full matrix as equal to false. And then it results in a faster computation. As you see here, it's few milliseconds as opposed to second. Then the U is not a full 4,000 squared matrix anymore, but you get the rest. So that's one trick. A better algorithm or a better approximate algorithm is gets you faster than computational methods. But here we look at another example here, computing the Fibonacci sequence. Fibonacci sequence is expressed like this. You start with 0 and 1. And the next item in the series is the sum of the previous elements of the series. So one approach is to use a recursive function. If you run that, you see that it works, but you can see visually as well. If I calculate fib recursion, that's fine, but quickly it blows up in computing time taken. For example, just computing 50 takes forever. And I'm just waiting for the answer to happen. So what it does, it exponentially increases in terms of function calls, or at least by a power law, it increases. What you could either do is to use a loop instead, and sometimes a loop is better. But there is another approach which is to use a cache. So in Python, there is a very nice decorator called LRU cache. LRU stands for least recently used cache. And this cache attaches to a particular function call. There are some conditions. The input of the function must be hashable. Typically, integers, floats, strings, those are hashable inputs. Arrays are unfortunately not hashable, but tuples are. So immutable data structures, just let's say that. So what LRU cache does is it computes the hash of the input and stores what the output is. And then the next time this function is called, it uses the hash. So here we are using a recursive computation. So every time the same input comes, it uses a hash instead of going through what the actual output is. So here you see that the 50, even though I'm using Lumi, it's not computed yet. So I'm just gonna stop that. Let's use this one instead. Cleaned up. And then fib cached. That's quite instantaneous, of course. It's one of the first few. And that's also faster now because of the caching. So that's a computational approach of optimization. But when you're doing with, let's take a look at what you can do to avoid for loops now. So in many cases, it might be easier to express an algorithm as a for loop. For example, here you are trying to compute the difference of an array into another array of a smaller size. And then you will think of, okay, let's just use a for loop here because it's easier to think in terms of element by element operations. But then it can take reasonable time for a small array, but it might be very slow when you're exposed to a large array. But instead, you can express this as a vectorized operation, and that should take you only a few microseconds as opposed to a loop. That's because the Python interpreter does not have to worry about every execution, and the whole computation happens in NumPy's fast C code. So that's something about vectorization. But maybe you have a expression which cannot be vectorized, and you only have a Python function which operates on a function of this a particular data. Let's call it X here. And you're using some functions which don't accept NumPy arrays. So for example, here you pass on an array, it says like, I cannot handle this array. You have to pass scalars. But to help with that, you should not try to use for loops again. You should try to use vectorize to create a vectorized version of this function. And now that function can operate element by element without a for loop. And this will still be somewhat interpreted, but if you want real performance, you can use Numba. The syntax looks roughly similar. For this particular case, it's Numba vectorize. The advantage is it will be JIT compile, so it will be faster. There are so far we have talked mostly about CPU time, but if memory usage is an issue, there are some tricks you can do. So when you're doing complex operations, it might result in intermediate arrays, which are very big. So instead of trying to expand an array, fill it up, you can try to use a vectorized operation. Here is a very small example. If you have an array and you need to add 4 to every element instead of building another array, which is B with size 3, you can use broadcasting rules in NumPy instead. these can get tricky. It's very easy to understand here, but here maybe it's not obvious like which axis it's going to be get broadcasted upon. But here you see what's happening. And that's a little bit about broadcasting. Cache effects. So NumPy arrays are particularly row major, which means that extracting individual rows and doing computation along it is faster. So if you take a sum along a row, which is like for every column, so that's why it's column axis, which means you are taking one row at a time and then computing the whole sum. So that will be faster rather than computing along the column or the row. Yeah. But yeah, that's because it's easier to jump through given a row. It's easier to jump through the elements rather than jumping through columns. Here we talk about broadcasting again. For example, no, sorry. Here we are talking about a very large arrays and you have a complex expression. So for each multiplication, you will create a temporary array and that can overload your memory. So the solution is to do it one by one so that your memory doesn't get overloaded. It will be slightly slower because you're updating the array one by one, but that's what you have to do if you don't have sufficient memory. I'll skip this part. This is about broadcasting again. And finally, we have something about NumExpression. NumExper is a library which can be used in place of NumPy expressions. For example, here we have a very large array and we are trying to do some complex arithmetic on it. You can try to write the same thing that you will do in using NumPy arrays in a string. And then if you pass it to evaluate, that will be faster because it uses multiple threads and it does not, overload the cache so much. So it does some smart optimization under the hood, and you'll get you won't even have intermediate arrays stored in Python space. So that's part of the reason why this using NumExpression is faster. So to conclude, we learned that one should measure and benchmark to find what the bottlenecks are before one starts optimization. And optimization can be done through changing algorithms, optimizing for memory usage. You can add substitute for loops with vectorized operations, or you can use NumExpression to compile, or Numba or Cython to compile, which we will talk about in tomorrow. So that's it.